All right, everybody, welcome to video number 2, covering 9.2, which is our exploration into graphing in the polar system. So from video number 1, what we did was we identified and graphed some specific polar equations, mainly the very straightforward ones, and we converted between the polar and rectangular equations. We're not going to do that quite so much with this video, and you'll see why as we get into it. What we are going to do is we're going to spend a little bit more time graphing these polar equations by plotting some points. So let's jump into it. So if we take a look at example number 9. So I have the graph of r equals 3 plus 3 cosine theta. Now, let me explain why we're not going to really do as much of the conversions into the next, or into the rectangular system. If we multiply both sides by r, we get r squared equals 3r plus 3r cosine theta. And that's, if we work with it, we get x squared plus y squared equals 3r plus 3x, which kind of strange, but okay, let's look at that a little bit more. This is where we would go with it. And then we're stuck because we still have x's and y's. We have this r. Now what we actually can do is we could change that r into the square root of x squared plus y squared. And if you take a look at that equation, you're like, man, that's really, really ugly. And that would be the reason why we're not going to be doing a whole lot of work changing these into the rectangular system. So still kind of like useful to see, but at the same time go, all right, we're good. So for those people who really want to see more of those depth, I encourage you, please look into that, see what's going on. But for most of us, let's just focus on how do we graph this. If you do remember from the Desmos activity that I had you guys do, you should know what this shape is, and that shape would be a cardioid. So let me go ahead, go over to GeoGebra. This link, if you notice, I have the 3 plus 3 cosine theta in here. So let's focus on the rectangular graph. We should know that this graph ends up being a cosine graph shifted up. And so we could see that cosine graph shifted up on the rectangular system. There we go, we can see that cosine graph just a little bit better. More importantly, what's happening on the polar system? Well, at the angle of 0, we have our largest radius of 6, kind of like what we did before. And now as we go up to pi over 2, we have our radius of 3, which makes sense. That's kind of like that equilibrium point on the rectangular graph. And then as we go to pi, we end up with a radius of 0. So what ends up happening is we get this first half of what we call the heart shape, also known as the cardioid. And what is the cardioid? Just as an explanation as to what that cardioid does is, if you take a point on a circle and you rotate that one circle around the other circle, you end up with this cardioid shape. And some people are going, why do I even care about that? This is used in a lot of mechanics when you're talking about what's happening if you have a point that's on, I always want to say like a cam in a like automobile system, that as one point starts rotating, what's the wear and tear of that one point? Or if you have a particle on a cam and that particle stuck there, how is it going to affect the wear and tear? So there are a lot of different applications to it. How about if you're looking at revolution around the sun? I know that those are obviously two very distinct radii, but like what's your point on the earth as the earth's rotating? There's a lot of astronomy aspects to this as well. So with that said, this gives us our cardioid shape. Now our cardioid shape is going to occur when your A and your B values are the same. Once again, you should have seen that in your Desmos explanation or exploration. So I'm not going to go into as much depth here because you guys have already taken a look at it. What I do want to say is, how do I take this equation that I have, and from this equation, how do I create the graph? This is where knowledge of what happens if you have a cosine versus a sine is going to help. This is going to be the beginning of our symmetry exploration, that if you notice the graph that we have over to the right, this is symmetrical to the polar axis, and that is due to the fact that we have the cosine function. Cosine has that symmetry. If you remember with the circles, if you notice this circle also has a symmetry with the polar axis, and notice that's because it's the cosine graph. This one had symmetry with the theta equals pi over 2 axis, and that is because it's a sine graph. or sine equation. So knowing what cosine and what sine do and those symmetries help us actually understand how to graph these as well. So if I were going to ask you to graph, which of course you know I like to, what I would have you do is take a look at what are the theta values and what are the radii that come out of these. We are going to look at where does cosine, or what is the cosine of 0. So all of our quadrantal angles are going to be very, very important no matter what we do. But then I also asked for, well, let's go ahead and list these. So this one would be 3 plus 3 times the cosine of 0, which is 1. This would be 3 plus 3 times 0. And then this is going to be 3 plus 3 times negative 1, which is 0. So at an angle of 0, I get a radius of 6. At an angle of pi over 2, I get a radius of 3. And at an angle of pi, I get a radius of 0. Those 3 points are kind of like the backbone of what this cardioid looks like, as you can see over to the right here. But it's not as helpful for us to graph it based off of just those 3 points, because anything could have those 3 points as shape. A lot of different things, probably not everything. So this is where I say I'm working with cosine, so my pi over 3s are going to come into play. This is going to be a radius of now 3 plus 3 times 1/2, which gives me 4.5. So if I follow along my pi over 3 and go out a radius of 4.5, I get that point. If I use 2 pi over 3, I will get 3 plus 3 times negative 1/2, which gives me a radius of, I almost wrote 1.5. Let's be consistent to say 1.5. So as I follow along my 2 pi over 3, I end up at that point. And so this is where we are going to kick in the graph. And our graphs don't always have to be perfect, but that it would be 1/2 of our 1/2 of our cardioid. Now the other half, this is where we could use the whole aspect of symmetry with the polar axis. If we continued on to say 4 pi over 3, we are going to model what's going on with 2 pi over 3. So that'd be 3 plus 3 times negative 1/2, or 1.5. So we generate 1.5 again. If we go 3 pi over 2, we will get 3 plus 3 times 0, or just a radius of 3. If we go 5 pi over 3, oops, did not mean to make that line. This would be 3 plus 3 times positive 1/2, or 4.5. And then 2 pi will once again give us a radius of 6. So because we prefer you to work on efficiency and not sit here and plot point after point, those point after point, very, very effective, especially as you're establishing what the graph looks like at the beginning, but it ends up being a little bit less effective towards the end. Go ahead and grab that side of it now. So what I would typically have you do inside of the classroom is I would have you say, I know what the symmetry is. I know this is symmetrical to the polar axis, and that symmetry is due to the fact that it's cosine. And then I would graph the upper half of the points and then use the reflection to graph the lower half of the points. For your homework assignment, what you're going to be doing is you're going to be looking at what does that equation give you, and then you're going to get to pick and choose from a series of those points. So it's going to be a lot less physical graphing for you as my students, but I still wanted to go through and say, how do we create those points if we were in a regular classroom? So 4 minus 4 sine theta, as I take a look at this one, first thing I'm going to note is these variables are the same, or these numbers are the same. Since these numbers are the same, that's what creates the cardioid. And now, because it is sine of theta, this has symmetry to the theta equals pi over 2 axis. Wrong tool. So symmetry to theta equals pi over 2 axis. And so what's going to happen is, as I go to graph my points, I'm really going to graph my points over here in quadrants 1 and 4, and then I'm going to reflect them over to quadrants 2 and 3 because of that symmetry. So because of this, because I'm going to be working in quadrants 1 and 4, or what I like to refer to sometimes as quadrants 1 and negative 1, what I'm going to do is I'm going to create negative pi over 2. I will work with negative pi over 6. And for those people asking why negative pi over 6, that's because it's sine. then 0, pi over 6, and finally pi over 2. This is now 4 minus 4 times negative 1, which gives me 8. This is 4 minus 4 times negative 1/2, which is 6. 4 minus 4 times 0, which is 4. 4 minus 4 times 1/2, which is 2. And then 4 minus 4 times 1, which gives me 0. So at negative pi over 2, I have a radius of 8. Along negative pi over 6, which is along here. So at negative pi over 6, I'm going to have a radius of 6, which would be right too far, right there. At 0, I have a radius of 4. At pi over 6, I have a radius of 2. And at pi over 2, I have a radius of 0. So let me actually graph this in the order of the points that get created. So here is my cardioid shape. And then this is where I say we can reflect that to the other side due to the symmetry. And that's why symmetry is so beneficial for us, because it allows us to graph that much more efficiently. And I'm probably making this a little bit more heart-shaped than, and in fact, I know I made that a lot more heart-shaped than it really is. There we go, that's a little bit better. So the shape is what we call the cardioid. And the general form is if I have r equals a plus a cosine theta. Now this cardioid, we like to say, is on the polar axis. And that is due to the cosine, where this one is the cardioid on the theta equals pi over 2 axis. And that would be r equals a plus a sine theta. Now, we probably should say plus or minus. And one of the nice explorations that we could look at is what happens if this were 3 minus 3 cosine theta instead of 3 plus. If I change that, if you notice, it changes the orientation. So to graph the second one that I did, if this is 4 minus 4 sine theta, so 4 minus 4 sine theta, that's the graph, at least that's a portion of the graph of what we've seen. Now, what happens if we change this from a -4 to a +4? That should actually cause reflection up into more like the bigger side in quadrants 1 and 2. That's because of the plus. And this is where, working with numbers helps you understand when we have a positive radius, when we have a negative radius. That's why plotting those points is very, very critical. Now, fun thing to do is to say, what happens if I make this a -4 instead of a +4? What happens to the graph? Nothing. The graph ends up looking the exact same. Now, if you notice, this point B, which is matching up with 2 theta, is now over here as opposed to over here. So even though the graph looks the same, it actually is generated very differently. It's generated starting in quadrants 3 and 4, and then it goes into quadrants 1 and 2. So let's go back to our notes. So if we have r equals 3 plus 2 sine theta, so if we notice A and B are no longer the same, what's typically we call these A and B, these numbers are not the same. So one of the explorations that you guys looked at in Desmos is what happens when these are not the same. So 3 plus 2 sine theta, let's go to this graph and say, what is 3 plus 2 sine theta? What does that look like? Now I'm going to shift this down so we can see the graph of this rectangularly. And if you notice, we do have that, that 3 is our equilibrium of 3 here. And that would be why the graph was shifted down, because I was scrolled down a little too far. All right, so if I take a look what this graph looks like, if you notice, and let me move this down so we can see it a little bit better. If you notice, this is no longer a cardioid. Now it has kind of like that same hardish shape, but what distinguishes a cardioid from this graph is there is no sharp point at the pole. Now that sharp point gets created because we end up with a radius of 0. Knowing that a radius of 0 occurs gives us that we have that point on the pole. But if we could see on our rectangular graph that we know we never actually have a radius of 0, our radius ends up always being positive. That is why we end up with this shape, which is what we call a limacone. And if you notice, I have this open on Wikipedia, that this limacone gets created, and this is where astronomy kicks in, also more work into mechanics. If you have like a center of mass, how's the center of mass affected as you have one ball rolling around another? That would be a nice application of it. So definitely a lot of physics involved in working with the polar system, which is why the polar system ends up just being so much more efficient in the long run. So I know it's less familiar for us, but it ends up being more efficient. So how do we graph this? This is where, once again, as I make my quick points, I start off with what happens if I have my theta as 0. I always like to look at my quadrantals. Now, because this is sine, maybe I should work with quadrants -1 and 1. So I'm going to take that back. Let's go negative pi over 2, negative pi over 6, 0, pi over 6, and pi over 2. So this is 3 plus 2 times -1, 3 plus 2 times -1/2, 3 plus 2 times 0, 3 plus 2 times 1/2, and then 3 plus 2 times 1. So my smallest radius occurs up here with a radius of 1, and that's at an angle of negative pi over 2. This one will be 3 minus 1, which is 2, and that would be at negative pi over 6. 3 plus 0 at an angle of 0. 3 plus 1 at an angle of pi over 6. And then 3 plus 2 at an angle of pi over 2. So my smallest radius is 1. My largest radius is 5. And that's really because once again, I never have a negative radius. Because I never have a negative radius, the graph never actually hits the pole. And since the graph never hits the pole, then it's what we call the limacone. So this is a limacone. There is a, the French, I wish I could remember the name off the top of my head. I can't, but anyway. So we have our limacone. Now this is limacone with no loop. And in the exploration, you saw some that actually had a loop. And the reason for that is because we have R equals A plus or minus, we could say plus or minus B sine of theta, or R is A plus or minus B cosine of theta. Now A is bigger than B, which is where that no loop comes into play. So where this one does not have a loop, this one will also be a limacone, but this limacone will have a loop. And let's actually, rather than jump to the graph and what this graph is going to look like, let's plot some points to see if we can determine what's going on. So because this is cosine, I'm going to work with symmetry over the polar axis. So I'm going to start at 0, pi over 3, pi over 2. And again, I'm using pi over 3 because it is cosine of theta, which will give me a ratio of 1/2. 2 pi over 3, and then pi. So let's figure out what our radii are. So at 0, I will have 2 minus 0, which is radius of 2. Pi over 3, it would be 2 minus 4 times 1/2, which is 0. Pi over 2, I have 2 minus 4 times 0. And just occurred to me that I had those backwards. So this is 2 minus 4, which is negative 2. 2 minus 2, which is 0. 2 minus 4 times 0, which is 2. And let's continue on. 2 minus 4 times negative 1/2. So that is 2 plus 2, which is 4. Then 2 minus 4 times negative 1. So 2 plus 4 is 6. Let me plot my points. So at an angle of 0, I actually have a radius of negative 2. At an angle of pi over 3, which is in this direction, I have a radius of 0. So what happens is this graph will come here. At pi over 2, I have a radius of 2. So I get this portion of the graph. At 2 pi over 3, which is in that direction, I have a radius of 4. So we're going to extend this a little bit further. That's not curved enough for me. So let me try that one more time. So it comes like this. That's better. And then at pi, I have a radius of 6, which will be right here. So this graph gets extended like so. So, and then if we bring symmetry into the equation, symmetry would cause our symmetry over the polar axis, which would create these points. And so as I continue my sketch, it'll look like this. Pardon the poor sketch. So this is what we call the limacon with a loop. So limacon with a loop. Now, the important thing that I want to say is what causes the loop. What causes the loop is this negative radius. So more specifically, the fact that we have a negative radius means that we are going through the pole, and then we create that negative radius. Now, here is a, not there, a little bit further down. Here is a visual of where that limacon with the loop actually comes into play. This is something I can look at over and over again just because it's fascinating to look at these tangent lines, what's occurring. But anyway, going back into the notes, if you know what, let's look at this. Let's look at our GeoGebra. And if I graph 2 minus 4 cosine of x, as you can see, we do have that limacon with the loop, and to see it created a little bit better. And by the way, that's the last one I'm going to do just by plotting points, just because this we're going to use our technology efficiently. It's when rectangularly, notice we had a negative radius here and we have a negative radius here. That negative radius is what's creating this inner portion of the loop. And that inner loop will always occur if A is smaller than B. So if I change this to a 3, we should still have a loop. If I change this to a 1, we should still have a loop. Now the fun thing is what happens if I change that 1 to a 0. If you notice, it's a circle. So really it's kind of like 2 loops overlapping each other, which is very, very cool to think about. That's really a limacon where both loops are the same. So a circle is a limacon where both loops are the same. Now that's probably not technical, but as I said, it's still kind of fun to consider. And then what happens if that A and that B value are the exact same? Once again, we have the cardioid. If A is bigger than B, then that's what creates the limacon without a loop. So I think that these are a lot more fun to actually play with. I mean, you saw me doing some playing with what happens if the numbers change. I strongly encourage, as you get to know the coordinate system or the polar system a little bit better, kind of play with it, see what's happening, which is where I'm going to give my hidden gem of I'm going to have students, for those of you who are listening and have made it this far, those students who have, I want you to play with GeoGebra and come up with a very fun shape and email me a picture of the shape with the equation that generated that shape. And I will have this as an extra credit that I'm going to put the extra credit on Canvas for all of you to judge and say which one that you like the most. So there's the hidden gem for today. So this limacon with a loop, as I mentioned before, is created when we have r equals a plus or minus sine theta, or r equals a plus or minus cosine theta. And I forgot to include the b there, where a is smaller than b. All right, next style of graph. Some of you were very, very familiar, or you saw this when you were working on the Desmos application. R equals 2 cosine 3 theta. Let's actually graph that right here and see what's happening. So 2 cosine 3 theta. This is what we call the rose. And now the rose has 3 petals. And just like some of the other shapes that we worked with, those 3 petals, you could see that they end up getting traced 3 times, or traced over itself. So what occurs is there are actually 6 petals here but we can only see 3 of those petals, and that's because of the repetition. Now, if we change this 3 to a 4, you'll see that we're going to have no longer just 4 petals, we're actually going to have 8 petals. And so what happens with these 8 petals is we get 4 petals traced, or at least the equivalent of 4 petals traced when we get to pi, and then we get the other 4 petals traced when we get to 2 pi. So by changing this number from an even to an odd, this is an odd, say this is a 5, we're going to have 5 petals to this. If this were a 6, we should see, as it's even, so we should see 12 petals. And once again, I encourage a little bit of playing so you can see, you can take a look and see what's going on. So what's happening on the rectangular system is this frequency creates additional loops. So this frequency, this cosine occurs 6 times. Therefore, it's going to create a series of 6 loops, positive and negative radius, which is why we end up with 12 loops overall, or 12 petals to this rose. So this is a rose, and roses are definitely a lot harder to graph. So I'm actually not going to graph it on here for you. If we were in class, I would do some of that work. But this causes us to have a rose, and we see 3 petals on that. Because it's cosine, the beginning petal, we actually will see on the polar axis. So let me go ahead and just graph one of these petals. It's hard to graph all of them, which is one of the reasons why I'm not going to do that for you. So we have a rose, and this is going to be a rose over the polar axis, or symmetry to the polar axis. And that symmetry to the polar axis is due to the fact that it's cosine. So that would be R equals some constant times cosine of a theta. Now, if A is even, there are 2 A petals. If A is odd, there are just A petals that we see. And that's because you actually see them go over, you see them graphed twice. Now, for example 14, where we have sine, if I do 3 sine 4 theta, so that one was our cosine graph. So if I do 3 sine of 4 theta, so 3 sine of 4x, if you see, we no longer have a petal that's actually on the polar axis, but we have that symmetry to the theta equals pi over 2 axis. We actually still have polar axis symmetry, but that petal is not on the polar axis. So this one, the sign forces us to have symmetry to the pi over 2 axis. And video 3 is going to go into our algebraic aspects of the symmetry. This is just kind of like your intro. If we change the number out in front, I could have done this with the other problem. If I change this to a 5, what that does is that increases the petal length to 5 because our largest radius ends up being 5. We could see it rectangularly up here. We could see it polar over here. If I change this to, let's have fun and change it to 20, which should tell us how many petals we see. 40 petals. Wow, that's all 40 petals. And to have even more fun with this, if I make this a, let's say 5 plus 5 sine of 20 theta, actually, let's make that number a little bit smaller. Let's make that 2, make this 3, so we have an overall radius of 5. We start seeing a lot of fun things happen right there. And I say fun just because I think there's a lot of fun here. What's actually going on is we have these teeny tiny petals here, and that's because since 2 is smaller than 3, we end up having negative radii giving us that. If I change this 2 to a 3, if I change this 3 to a 2, then we end up having what looks like what we call the normal flower, where there are no inner loops. And that's again because our largest number here is going to be 2, our smallest is -2, so we never have a negative radius. So as we look at our Cartesian graph up here, we never have the negative radius. So we get the nice fun flower petal. As I said, I like to play with those graphs. Now, what's the important thing for you to know? This creates a rose for us with 8 petals. And we have symmetry over the theta equals pi over 2 axis. So rose, I probably should have just written that down here. So rose symmetry to theta's pi over 2 axis. And that would be r equals k sine of a theta. And once again, this is where I'm just going to take what's over here, copy it, and paste, because all that information is still relevant. Now, the last of the shapes, so we worked with cardioids, we worked with limacons with and without loops, we worked with roses. The last shape is called the lemniscate. So our lemniscate, L-E-M-N-I-S-C-A-T-E. The general form we now have r squared is a cosine. And for our lemniscate, we're just going to keep this as 2 theta. So r squared is a cosine 2 theta. This is not something that we can graph on GeoGebra because of the r squared. But what I could do is I can graph it as the square root of 9 cosine of 2x, or 2 theta. And so this is our lemniscate. It's really kind of like that infinity sign. Now, again, what I like about this is, if you notice, the graph in the Cartesian system doesn't actually graph over here. And that's because from pi over 4 to pi over 2, cosine will then be the cosine of an angle between pi over 2 and pi, because we double it. And so this is negative, and we cannot take the square root of a negative value, which is why there's no graph showing up down here. So as I continue with my Cartesian, suddenly at 3 pi over 2, I start getting a graph again. But here's where we'll have the square root of a negative, square root of a positive, and so we only have half of this graph. Now, let me focus on the polar graph. What happens is, because there is nothing rectangular, there is also no polar graph, and so we have one of these petals of the infinity. So what had happened is, in the imaginary plane, we actually had a petal showing up right here, and now we're creating the second petal. And then in the imaginary plane, because of the square root of a negative, we're creating another petal, and then we're completing this petal right here. So what's important for you to know is this is a lemniscate, and that lemniscate is on the polar axis. So lemniscate on the polar axis. And the last connection I want to make is this 9 will end up giving us a radius of 3 as that lemniscate. So this petal has a radius of 3. Now, it's not a rose, and I'm definitely not doing this graph justice, which is why I typically, I want to show the graphs in class. We would do more work with it. But since we're not in class, since we're online, we're not. So this, the largest petal, or at least the largest point on this petal, would be a radius of 3. Now this one, the largest point would be a radius of 4. Now what I would like you to see is, if I do this as the square root of 16 sine of 2x, what's occurring is we have this shift. We're no longer on the polar axis. We're actually at a 45-degree angle. So we could see same thing happen, that we have some points that don't actually exist. So we have petals. This really has 4 petals, but 2 of them are in the imaginary plane. We only see 2 petals. So with lemniscate, we only see A petals all the time. A meaning like that coefficient, petal all the time. There are a lot of students who always ask me, well, you only dealt with the positive square root. What happens if we have the negative square root? Before I get into that, let's kind of see how this gets developed. So we see the full petal, imaginary petal, full petal, imaginary petal. So what happens is this graph gets created here. There actually is an imaginary petal down here. We now graph this one, and then we graph that one. It's an imaginary petal. If I make this negative, how does that change the graph? It actually doesn't, surprisingly enough. But what happens is how this graph gets generated. There we go. How this graph gets generated, we now generate that quadrant 3 petal because of the negative radius first. Then we generate the quadrant 1 again because we always have negative radii. So just to finish touching up our notes, we also have a lemniscate here. So the lemniscate, now this is on theta equals, I'm going to put the pi over 4 axis, and that's because of the sign. That's half of the pi over 2, and the reason why we have half is because of the 2 theta. No, I'm not expecting most people to know that, but I just wanted to kind of explain that. And the general form of this shape is r squared is a sine of 2 theta. Hopefully this gave you some insight into what the different graphs look like and why they're created. And so stay tuned for video number 3, where we're going to go into a lot more depth about how we actually show that symmetry.